Okay, welcome back on another session on this track. I'm together with Anton Arhipov, who is developer advocate at JetBrains, and Anton will deliver today for us a presentation under the title Debugging Application with Intellij IDEA. And as always, at the end we will make a short Q&A session, so write your question to Anton on a chat and I will pass them to the Anton. So everything from my side, and Anton, the stage is yours. Let's start the show.
Thank you very much. Hello, everyone. Yes, my name is Anton. I'm a developer advocate at JetBrains in Kotlin team, but I've been using IntelliJ for about 20 years now, and I know a lot of tips and tricks, and I love the debugger. So today I want to share some of the useful features that you might be, able to use even today or the next week when you actually work in your code. It might not be obvious from from my presentation or from the way I described it. Debugger is not a productivity tool. It doesn't make you productive. To make you productive, you should be writing good code and writing tests, and then you don't spend time debugging. But well, the perfect code is not always written by you, and sometimes it's written by someone else, and you need to make sense of it, and you need to debug it, and then you probably would like to know some nice features in the debugger to quickly get over the situation. So I will have like multiple examples where I will demonstrate those little tips and tricks in IntelliJ debugger, and we will start with an example that is not directly a debugger feature. Actually, it's a feature of a JVM runtime, but the way it's usually used is in the IDE debugger, be it IntelliJ, NetBeans, Eclipse, or any other tool. This feature is available to you, but the way the workflow looks like is dependent on the IDE, is dependent on the tool. So in this example, I have a looping program that just calculates something and prints out into the console. Uh, there is an infinite loop. There is a value calculation. Basically, we can concatenate a string. The program sleeps for a while and continues doing something in the loop. So let's run the program and see how it behaves, what can we do with it, how we can inspect the various variables and things, and probably you will learn something already from a simple example. So let's start the debug mode for this program. We don't have any breakpoints. The program runs. We can see that it is running, right? But nothing is happening. And at this point, you might think that the program hanged. And how do we figure out what is it doing actually? Uh, in the debugger window, right in the toolbar, there is a nice button called pause program. So if you call that, it will actually pause the program, pause all the threads, and you will be able to see where the program is currently standing, where is the program pointer. Uh, and we can see that it's waiting for the bytes function, read bytes function. So probably it reads something, and we can confirm that by observing the stack trace, read bytes, read, right? That's my function. That's the read function that I wrote in my program, and then we can see that this function was invoked from get value function that calculates the result that we want to print, and then it was invoked from the main function. So we now know the state of the program, and we can do something about it. We can actually let it go in multiple ways, either click the resume program again, or in the latest IntelliJ, we have the new buttons on the side, like small buttons on the same line. So if you want to continue, you can just resume the program, or if you know the shortcut, of course, F9 will do the same. So if we just let it go, the program will still be, waiting for the input. And if we look into the place where it's reading the bytes, that's the read method. We can set the breakpoint somewhere in this method and satisfy the requirements for the program by entering something from the terminal. So since it's waiting for the standard input, A, B, C, D, E, and as the program continues, it hits the breakpoint that I just set. And we can see that on the right-hand side from all the statements, we can observe the values that are available in this frame. And we can even do something about them, like maybe change the value, or maybe want to change the behavior of the program so that the next time when we hit this method, when the program tries to calculate the value, we wouldn't wait for the standard input, for instance. We don't want to wait for that. So we could comment out the statements that are required for reading the user input. And if we recompile the program like this, compile and reload the file, what will happen is that the compiler will create the new bytes on the disk, and that will signal to the debugger in the IDE that there is a new version of a class that we could push into the runtime, and that will trigger like a small dialog. So if we do that, we can see that two classes reloaded, because I have two class definitions in this file. So there are new bytes for the two classes on the disk. The IDE pushed it to the runtime, and everything was great because I only changed the internal statements of the method. I did not introduce any new methods or any new classes, or I didn't change the shape of the classes. So this kind of change is compatible with the with what the runtime can do. Basically, this function is called hot swap in the JVM. So now it should work. The thing is, it will not immediately take effect unless until we actually drop the frame or exit the frame and enter it again, enter this same function again, because we are changing the same function where we are currently standing. So if I just let it go right now, like F9, and run it again, you will see that the previous value was printed, but on the next entry, our program does not read or does not wait for any user input. That's expected. That's the change we introduced. And we have a new behavior, right? So now the value is calculated without the dashes in between the values. And we can experiment further. So the first change in, or the first behavior, or the first tip that we have here, is that we are able to reload the class behavior. Like, we changed the application and we now have a new behavior. But sometimes we are not able to change the source code. Maybe the source code comes from a library, or we don't have control over it. And then sometimes we need to change the behavior while debugging, and to kind of emulate a situation. And imagine that's the case, and I, for instance, want to change the return value of this function because the calculation logic is slightly too complex, but I just know what kind of value I want this method to return. And I can do that just by setting this value of the builder. Or like, yeah, there are multiple options actually. I could have set the builder variable itself. If I expand this inline hint with the value, I can call set value function by F2, or just using the mouse click, and say that there should be the string builder with my value instead of the 1, 2, 3, 4. And if I let the program go, F9, I will see that the new value that I have assigned for this variable was returned, and it was printed out into the console. That's a temporary change, but it kind of works for me this time. Or the other way to do kind of the same, if you don't know how to set or where to set, maybe there's just too complex logic and you want to immediately return from this method without getting to the point where you can set the value. While standing inside some method at some breakpoint in any place, you can actually call force return in the debugger and just provide your expression or any other value to be returned from this function. So if we want to return some specific value, my value number 2, I can just force return from here, and you will see that the value that is printed into the terminal is the one I have assigned. Another way of changing the behavior when we are somewhere in standing somewhere in the function, for instance, is rolling back. So you have debugged some of the logic, and you lost the trace how you got there, or you want to restart the calculation, you don't want to proceed, you would like to enter this method again and start over, but without starting over the whole debug session. It's possible to drop the frame from the stack trace, or we call it actually reset frame. There's a little icon on the left, as you can see, that you can just press, and what will happen is that the frame on the stack trace will be dropped and we will enter it again. So we kind of going a step back in our program execution. And if I enter it again, you can see that no value was actually, let me enter or like execute this program again, continue. So no value was printed. So we actually rolled back and now we are entering it again. So these are kind of tips and tricks for changing the behavior during the debug session. So you can experiment, you can kind of tailor the program and adjust its behavior for your own needs. Another last thing that I want to demonstrate here is that besides forcing the result of the function, you can also experiment and see what will happen if there is an unexpected behavior happening in the program. So instead of force return, we can throw any exception, even if the function does not actually declare that it will throw an exception. We can emulate what will happen if it actually throws an exception. So instead of returning a value, I could throw an IO exception here, my error, and we'll see how the application crashes. So in some situations, you might want to emulate this behavior and see how your application survives. So if I click OK, there will be the last unhandled exception handler, where we set an automatic breakpoint for you, so you could inspect the application state before it actually goes down. So we could see that, well, what happened with the thread, what was the exception stack trace, and so on. Sometimes you might want to iterate over the heap. It's also possible. So now it actually crashes, and if I let it go, the program will stop. So this is the first example I have for you. I hope there are some little tricks that you already discovered for yourself if you didn't know them. Let's continue with the other examples. I have another one about the breakpoint. So most of the tricks I will show today will be around the breakpoints because there are so many settings and there's so many things you can actually do with them. Consider this example with the stream expressions when we got uh, Lambda expressions with the stream API in Java 8. Um, it became fancy to write expressions in one lines, so we started writing those transformation chains like filter, map to list, and so on. And quickly, people figured it out that it's hard to debug them because when you have everything written in one line, it's not really convenient when you need to debug specific place in that pipeline. And usually the debug points or breakpoints are set to a specific line. So if it covers the whole line, it's not possible to set to a specific Lambda expression. And then people started to break the lines into separate lines, right? Breaking those chains. In IntelliJ, you can actually set the breakpoint to a specific expression. So not on a full line, but in a single Lambda expression in that pipeline. So whenever you try to do that, whenever you try to set a breakpoint, the editor or the IDE will detect that on that specific line, we have multiple expressions, and then it proposes you to select one specific place where do you want to set this breakpoint, either on a full line or to an individual Lambda expression. So if we do that and we start the debug process, we will see that it hits a specific Lambda expression. So not the full line is highlighted, but only that single place. And if we do step into, it will actually jump to the next expression in this pipeline. F7 jumps to the next one, to the next one, to the next one, and so on. It's fun, but it's also not very productive. You can inspect very in very small details what is happening in the single expression, but it doesn't give you the whole picture of the logic of this pipeline. So there might be slightly better ways of debugging such places in your application. If we set the breakpoint to the full line, we will be able to do this debug in slightly different manner. So if I run the debugger again and I hit the line in the debugger, this time it's a full line, not a single expression. And if we try to do stepping, the IDE will detect that, okay, we are trying to do stepping on a line where there is many expressions, and it will ask you, where do you want to go? So F7 again. And now you can see that some of the places in this line are highlighted, and with using the arrow keys, we are able to select the specific place, either to go to some of the methods that are in the chain or to some expressions that are used in the parameters as Lambda expressions. So if I jump here, I can jump into a specific place. It's slightly better than the previous example, but there is even a better way of doing this. There's an action called trace current stream chain action. So when your debugger stops at the line like this, where you have a stream chain, where you have the stream API, you can have this trace current stream chain action enabled, and if you click that, it will evaluate the values that the stream received, and it will visualize the individual operations step by step. So in this case, I can see that there is an input on the left for the stream. There is a filter operation. After the filter operation, I will see that one value has gone from the stream. Then on the next filter, another value disappeared from the stream, and then there is a map function that maps the initial input for that operation into some other object, right? So I have created from the string, I have created a user object, and then there is a final result as well, which is a list of those user objects. And you can use the split view mode for the individual operations and visualize it like this. This is a slight, like, also it's a better way of understanding the whole picture, how the stream works. But you have to acknowledge that this is not on the fly evaluation, right? So if you supply a huge input file as an input for the stream chain, it will have to evaluate all the values. So we need to limit it somehow. So maybe you will need to adjust either the input, or you will have to wait until the stream evaluates. And if it's a file that, you know, is so huge that it doesn't fit into memory, then maybe you will just crash the IDE. Okay. So I hope this one is also useful for you. Let's proceed to the next example. The breakpoints. So usually people think of the breakpoints in terms of lines. So they set the breakpoint to a line, and they usually forget about the ability to set breakpoints to members. The members are the methods and actually the fields as well. So you can set a breakpoint to any field, and it will mean that the breakpoint will monitor the writes and reads to the field. But this time I want to show you how it works with the interface methods, because it's interesting in a way. The interface, when we look at it in the source code, it doesn't have any code, right? There's just a method declaration. And if we do that, let's say we set a breakpoint to this boo method that is used in my main method. If I execute my program right now, I mean in the debugger, I will see that it hits the breakpoint in the implementation, not on the interface. Historically, people try to avoid using the method breakpoints because they actually slow down your application very much, and they use it as a last resort. In IntelliJ, actually, we have emulation for the method breakpoints turned on by the default. So the emulation behaves in a way that it kind of behaves like a method breakpoint, but it actually sets a breakpoint to the first line of the method. And the editor will actually demonstrate that as if it's a method breakpoint, not a line breakpoint. But okay, that's impressive that you can set a breakpoint on a method and it doesn't slow your application down. But in this case, we could have reached the same result without the method breakpoint, because we know that the boo method is invoked via the main method right here. So if we didn't know about method breakpoints, we could have done this way. We could have set the breakpoint at this line, run the debugger the old way, hit the breakpoint, do a step into. The debugger will ask, where do you want to go? You select that method and you end up in the same place as we previously have seen. But this is only possible for you to discover if the method is actually used, if the editor can tell you that the method is used somewhere. But what if the editor tells you that the method is not used anywhere? In this case, this foo method, you can see that it's highlighted as gray, so it's grayed out. It's never used. So the IDE reports it didn't find any usages. But for instance, you can see that in the logs, or you can see some program behavior that clearly says that the logic by some of the foo implementation is working, is executing. So how do you discover that? we can set the breakpoint on the foo method. We don't know where is it invoked and who is calling it, and run the program in debug mode again. And we will hit some implementation, some invocation of the foo method. Why is that? Clearly, the IDE couldn't find the usages of that method invocation because it was actually invoked via reflection. Yes, there is a constant that evaluates to foo, right? I tricked the IDE so it couldn't discover the invocation. If I would have written this constant in one piece, like foo as a string, the IDE is smart enough to actually find it. But this time, the name of the method is a result of an expression, and this expression could be much more complex, like concatenation of multiple strings in some by some other method even. Then the IDE would not be able to discover it by static analysis, and you would not find the usages of that method. But using the interface debug breakpoint, I'm able to discover this place and clearly say, okay, there is a culprit. And if we go to the debug window, we can also observe that by looking at the stack trace, how it was invoked and who actually invoked it, right? So that's another trick for you. We can stop right here and see what else we can do with the breakpoints, because there are so many options. Consider this example here. We have the main method with a loop that prints out an instance of a singleton cache. So if we just run the program, not even in debug mode, we can confirm that the value or the instance of this class, of this cache class, is always the same. So it always prints the same reference. What if we want to debug the initialization process of this class, so we could start over without restarting the program? It's possible to automate setting a value in some other place without actually forcing the program to stop. So if we select the instance right here and do a shift click on the right hand side, the debugger breakpoint configuration will pop up, and it has unclicked the suspend checkbox. So it will not suspend the program when it hits the breakpoint, but there is some automation that you are able to add to this breakpoint, a non-suspending breakpoint, to change the program somehow. So this evaluate and log field, you can just run any expression. You can even have like a full program snippet in there that will execute, evaluate, and produce some value, which you will be able to print. In this case, for our purpose, I want to just reset one variable, this instance field. And if I do that and run the program again in a debug mode, then we will actually not stop. We will just print some values to observe how I change the behavior of the program. And the expected behavior is that the reference of this cache object will always be different. So we actually set the instance to a null. So the if expression evaluates to true, and we are reinitializing the cache again. So if we needed to debug the initialization project code for the cache, if we needed to debug the constructor over and over again without restarting the debug process, we could use this trick, of changing the state of the program, changing the state of the field, and trigger the reinitialization logic again. Okay, this is a non-suspending breakpoint, but what else you can do with them? Consider this example here. We have a complex workflow that receives some value, 1, 2, 3, 4. And we use this value to propagate through the program. So we propagate it as an ID, for instance, workflow process. The process calls step 1 in this workflow. Step 1 calls step 2. Step 2 calls 3 and 4. And at the very end, we have some logic that where you do something with this ID. When you get to this method by just navigating the code, if the workflow is complex enough, it spans multiple classes, you might not be, you might not remember even how you got there. So you try to roll back and see, okay, this method is invoked from there and so on. You can use some static analysis functionality by standing on this value that you are tracing and invoking data flow to here action, and it will analyze your code and see how the ID is propagated through the invocation chain on the whole project. And it will even detect that if you somehow change the name of this variable, so it doesn't matter. It will detect the changes, and even if the value is somehow composed into a more complex value. So we can clearly see that there are two branches in our code that consume this ID, or this is how we got here at the very end, and we started from the main method right here, and we can do it vice versa. We can call the data flow from here action that will visualize from the very top to the very end of the invocations, and there we will see that step 1 is calling step 2, 2 is calling 3 and 4, and so on. So now imagine the situation that we have this workflow spanning many branches, and we would like to stop at the breakpoint somewhere at the very end, but only for a specific branch. So for instance, we want to stop at this output method somewhere right here, only if this output method is invoked through the branch that spans across step 4, but not at step 3. So we can set a breakpoint, any breakpoint in the beginning, so doing it in a naive way. And then when we hit this breakpoint ourselves, we would unset it and set this last breakpoint in the point of interest, in the method of interest, and let the program run again. But there is a bit more efficient way of doing this using the non-suspending breakpoint. So the fact that we hit this breakpoint is actually recorded. So this breakpoint is currently doing nothing. It doesn't log anything, it doesn't suspend the program, but the fact that we hit this line during the execution is recorded in the IDE debugger. And now, if we go into the settings for the other breakpoint, we can say that this breakpoint could be disabled until we hit the other breakpoint, which is a non-suspending breakpoint. So we can select that other breakpoint that we set, which will act as a trigger. And now you can see we have two breakpoints. One breakpoint is dependent on the first one, and the first one is a non-suspending breakpoint. It will not stop the program. So once we hit that, the other breakpoint enables, and then if we hit that line, the debugger will stop there. So let's try. We run the process. We hit the breakpoint right here, and you can see the stack trace of the program and observe that, we actually reached this breakpoint via the step 4 branch. So it did not stop in the branch that was passing through step 3 in our program. That's a nice feature. So we have seen two features right now in one example. The static analysis feature, which was tracing the ID through the invocation chain and just giving us the report, the visualization, how the ID is propagated. That's called data flow analysis. And now the other part of it is setting the conditional breakpoint to the point of interest depending on some condition. The two features of the ID, the debugger and the data flow analysis, can be actually combined and presented in a way that when we stop at the breakpoint, when we evaluate our code in the debug session, the IDE can use the values to evaluate the data flow or probable, let's say, the conditions and the values inside the same frame. And it can immediately tell us, okay, this condition that the ID is not null, our ID is 1, 2, 3, 4, is going to evaluate to true, and it will highlight that in the editor. And it will also highlight the branches of the code that will be executed. So if the branch will not be executed, it will be grayed out here. So it immediately helps me to understand that, okay, in this complex method, those branches or those if and else's or maybe some loops will not be invoked. So I don't need to pay attention to them. Or maybe I should pay attention to them depending on the situation. All right, that's probably a nice example as well, and a nice hint for you. Let's look at the very last example I have for debugging concurrency. I hope I will have enough time to explain that. Concurrency bugs are pretty nasty and hard to debug. So I think it's important. In this test, I have a test, right? I execute the logic in 2 threads. So the logic is like this. We have a collection, and we want to add the same value to the collection twice. And our logic is of this program is that this same value should not be added twice. It's slightly contrived example, but it will demonstrate how you can debug the concurrency issue. So we are adding number 17 in a main thread and also in a additional thread. If we run this test, it will pass. It will most likely pass because, well, it's a simple code. It seems to behave correctly, right? We can run it multiple times, one by one, and 99.9% of the time it will succeed. The thing is, we ship this code, and in some time in production it will fail. How to discover that and how to confirm that? One option is to retry many times. So there's a repeat option for the tests. So you can run the tests once, or you can run multiple times, or you can run until failure. We can try running it until failure for a few seconds, because sometimes it actually would take you to run many times, quite a few minutes until the test fails. Let's try that. If we can wait until it.
Sorry that I interrupt you, but please let's finish slightly your talk because we are out of time.
Okay. Let me say one last thing of what I have shown. So I executed, and I can confirm now that the test fails. I will not have time to show you the debugger feature to debug this, but maybe next time. So thank you for watching, and if you have any questions to me, you can find me on Twitter. My DMs are open, and have a nice day and the rest of the conference.
Okay, Anton, thank you very much for your presentation. We learned a lot of useful tricks and tips in Intellij IDEA. As always, I encourage you to rate Anton's presentation using the stars under the video player, and see you after a very short break on the next session. So see ya.
Bye-bye.